Now to finish up equilibrium, we are going to do an example that, well, it's a little bit more complicated. The last two examples that we did, they had the advantage that there was A, only 3 vectors, and B, a right angle was able to be found in the vector diagram. So that opened up things like SOHCAHTOA, Pythagorean theorem. Now, what if we decide to say, well, there is no right angle in your vector diagram this time? Now some of you might say, oh, well, I know the cosine law and sine law. Alright, then what if I throw another wrench in your plan and say, well, guess what? This time there is 4 or more vectors, so you won't make a triangle anymore, and your precious sine and cosine law isn't going to work anymore. So we have to find a backup method. And I wouldn't even call this the backup method, I would say this is the actual proper method. So this method with the components, this has the advantage that it works every single time. So we're going to show you how this works. Now, I'm not going to be explicitly testing you on something like this just because it's a lot of work. I can test your knowledge of 2D vector resolution without going a little heavy on the math. Because as you're going to see, this question ends up becoming more an exercise in mathematics than it does in like physics. So I'll show you what's going on here. So we have a body, it's got a weight of 98 newtons, and it's going to hang from 2 strings that are attached to the ceiling as shown below. Determine the magnitude of the force of tension in each string. So this time, the lovely question, this is essentially a free body diagram, so we might as well just rip this free body diagram off and use it for ourselves. Now, let's call some directions positive. So let's call to the right and up positive. Now, for anything we're dealing with forces and components and all that, or rather forces in 2D, if the vector is not explicitly in the x or y direction, get its components that are. So for example, this S vector here, this is going to have an x component, we'll call it Sx, and it's also going to have a y component, Sy. Same thing with this t vector here. This t vector is going to have a component Tx, and it's also going to have a component Ty. So this is our free body diagram with all the vectors broken down. Now, because this is an equilibrium problem, or this thing just hangs there, it's equilibrium, we know that the net force acting on this sine is 0. So what we're going to do is we're going to work with that. Before we do that, though, we are going to break down our 2 vectors, and we're not going to be able to break them down and get a numerical value. We're just going to try to put Tx and Ty in terms of the tension itself, T, and we're going to put Sx and Sy in terms of T. So let me just sketch our 2 vectors here. So I have this T vector here. So this is vector T. We are told that this angle in here from the vertical is 60 degrees. So what that means is I can get this component Tx, or sorry, Ty rather, and then I can get Tx. Now, with T being my hypotenuse, Tx being my opposite, and Ty being my adjacent, what this is going to tell me is that Tx is going to be T times sine of 60 degrees, and Ty is going to be T times cos of 60 degrees. But now that we're breaking things into components, we'd better be careful with directions. So Tx is going to point to the left, but we have called right positive. We must put that negative in there. Ty is pointing up. We've called up positive. We can leave that alone, but we do have to make sure that that negative is in there. Otherwise, it's going to make a mess of everything. Now, in terms of our next vector, we have the lovely S vector. Looks a bit something like this, we'll say. So here's S, and then we're told that angle from the vertical is 40 degrees. So what that means is we're going to get this S of Y and S of X. With this angle being referenced from the vertical, just like with T, that tells us that S of X is just going to be this S vector times sine of 40 degrees. Sy is going to be S cos of 40 degrees. Now Sx points to the right, Sy points up. Right and up are what we've defined as positive. We can leave those alone. What we're doing is we're just kind of doing some of the work in advance. And let's start with this. So we know that the net force is going to be 0. We can check the net force in both directions because we know the net force in x has to be 0. The net force in y has to be 0. So let's start out with the x direction. So in the x direction, the only two forces in the x direction are my x component of s and my x component of y. So I know sx plus tx, those are going to be the only things in my x direction. Now, with this being an equilibrium, the net force is going to be 0. So I'm going to get sx plus tx equals to 0. Now, I know that 0, instead of sx, I can put this s sine of 40 degrees. Instead of tx, I can put this plus, I can add this negative of t sine 60 degrees. So let's now, plus minus, this is just the same thing as saying, minus. So this is really s sine 40 minus t sine 60. So what I'm going to do is I'm going to dump the t sine 60 to the other side. So I'm going to get t sine of 60 degrees equals s sine of 40 degrees. So for this, I'm actually in a bit of a bind right now. I have one equation and I have two unknowns. I don't know t and s. So for the moment, I'm going to stop this and I'm going to go to the other direction. Because we always said if we kind of hit a dead end in one direction, we can go to the other direction for a little bit of guidance. So let's look at the y direction instead. So let's look at my net force in the y direction. So in the y direction, I have the y components of s and ty going up, and I also have this weight going down. So I get sy plus ty plus this weight. But once again, I know that the net force in the y direction is 0 because this is an equilibrium. So I know sy plus ty plus the weight. So once again, what I can do here is I can solve, or I can at least substitute in what's sy, what is ty. So sy, I know is s cos of 40 degrees. Ty is going to be t cos 60 degrees. And then my weight is 98 newtons, but the weight is pointing down, and I've called up positive. So that weight has to go in as negative 98 newtons. So if I simplify this, I'm going to get something like 0 equals s cos 40 degrees plus t cos 60 degrees minus 98.0 newtons. Now with that said, I have two equations and two unknowns. I have s and t here, and I have s and t here. What I can do is I can actually substitute t or s from here into this equation. So what I'm going to do is I'm actually going to solve this for t. So we're going to divide both sides by sine of 60. And what I'm going to get is I'm going to get t equals s sine of 40 degrees divided by sine of 60 degrees. So this is an equation for strictly t. Well, I can take this equation for t and I can substitute that into my equation over here. So instead of writing t, I can write s sine 40 divided by sine 60. So you're going to see that this gets ugly really fast. What I'm also going to do is this 98 newtons, this negative, I'm going to put this on the other side. So I'm going to have 98 newtons. This is going to be equal, so here's my s cos 40 degrees plus, now instead of t, we're going to sub in that s sine of 40 degrees over sine of 60 degrees, and then I have that cos 60 degrees. So this is my new equation. It's pretty nasty looking, and we haven't even quite finished it yet. Now I have one equation and I have one unknown. I have my s here and I have my s here. But I have my s's on one side, so that's good, but they're in multiple terms. So I have to factor s. So I'm going to factor s on the right side. So we're going to keep that 98 newtons. I'm going to leave it alone. But now I'm going to factor out s. So here I have this cos of 40 degrees that's left over. And then on this side, what I have left over is I have this sine of 40 cos of 60 divided by sine of 60. So I can get s by itself at this point. I can divide both sides by this mess in the brackets. This is really nasty looking, but it will allow us to solve for s. So s is going to be this 98 newtons divided by this cos 40 degrees plus sine 40 degrees cos 60 degrees divided by sine of 60 degrees. So this is really, really nasty. Hopefully you can appreciate why I wouldn't be so inclined to ask you this on an exam, just because at this point it's becoming more of a physics question. It's becoming more of a math question than it is physics. And at the end of the day, as a physics teacher, my job is to help you out more with calculating. My job is to help you out dealing with physics, not so much dealing with this kind of stuff. It's not so much dealing with like intense math questions. So if we calculate all that and we're really careful, what we're going to get is about 86 newtons. Now, I have a value for s, so because I have that value of 86 newtons, this is going to allow me to now calculate for t, because I can sub this 86 newtons, I can sub that into t over here. So with that, I know that t is going to be this s value, so about 86.180 newtons times sine of 40 degrees divided by sine of 60 degrees. So if we calculate that and we're really careful, we're going to get about 64 newtons. So the last thing to wrap this up, we could say that the magnitude of s is about 86 newtons, magnitude of t, it's about 64 newtons. So this is a very labor-intensive question. There's a lot going on here. But this is just meant to highlight the methodology of what we do in the event we can't get a right triangle with our vector diagram. So that concludes dynamics. Well done.